Guys, this video needs a little bit of an intro. So I had a power supply to repair. This is the PCB out of it. It's a slightly unusual construct, this one. I wasn't very familiar with it. So when I try to repair something I've not seen before, I usually try to figure out how it works first. So once I understand the basic operation of it, then I can take it from there. If I don't have any schematics, I generally do that with data sheets, sometimes just with experience, having seen similar things before. But sometimes I find something which really is unfamiliar, an unusual way to make something basically. So this is an example. So if you watch through this video, this is mainly me trying to figure out how this thing works. It's a good example that when you're doing this sort of thing, you'll sometimes get it wrong or go down a bit of a blind alley and then figure out that you were wrong and head in the right direction. So that's what you're going to watch now. Hope you enjoy it, and I'll see you all at the end. Hi guys, welcome to Learn Electronics Repair. Let's look at a power supply today. Not done any power supply repair for a little while. This is a lithium-ion battery charger from an eScooter or eBike, 42 volt out at 2 amps. Okay, it has this connector on, so this is not just like a power supply that you could just get something else of that rating. It has some sort of sense pins in here as well. So we need to try and fix this. Getting one of these original types is probably quite expensive. I haven't looked, but hey, fixing it is going to be fun, one would think. Yeah, and that's what we're here for. So first thing first, when you get something like this connected with a light bulb in series, a current limiter, you can build these yourself. I've made videos about it. For anybody who hasn't seen how to do that, look in the video comments, you'll see how to build yourself one. There's two reasons for this. One, that if this is short, it's not going to trip the mains out or blow any fuses. The light bulb will just come on full brightness. And two, because the way the bulb behaves will tell us a little bit about what's going on. It's a useful diagnostic tool. So let's see what this one does. And there it is. So if this comes on bright and stays bright, there's a short in here somewhere. If it doesn't light at all, then this is just open circuit, no power's getting into it, or at least not as far as the main capacitors. And if it comes on bright and then goes dim, it's powering up basically. So this will tell us straight away, pretty much. Let's switch it on. It went bright or flash, then went dim. So that tells me this is powered up. It also tells me that the large capacitors in here will probably be holding a charge. And it looks like this is actually, to some extent, functioning. So, being difficult to probe here, I'm not sure which pin is which. If I can open it up easily, I will do so, and we'll have a look to see what's what with this. And yeah, it has screws in here. Okay. There we have it. So this is the large smoothing capacitor or bulk capacitor. This could have a high voltage in it. Let's have a look. If it stays charged, that would suggest that power's getting in as far as enough to charge the capacitor, but nothing's running, so it can't discharge. So let's see. It has 13 volts in, so it is discharging. Let's power it up again, and then see how long it takes to discharge. Okay, so on, switches off. In fact, there's a green LED on here. Can you see that? You can't. Look. This is working, basically. Let's see what's coming out of this then. 33 volts. Okay. Question is then, if this is supposed to be a 42 volt supply and this only has 32 volts coming out of it, although there's no battery attached, that would suggest it can't generate enough voltage to charge the battery. Okay guys, so Det just wandered in and he has the electric bike, eBike, and this is his battery, which actually fits his charger. He has the same sort of charger. So I've connected that. Now Det tells me that the green light coming on is a bad thing, not a good thing, because that means the battery is fully charged. Yeah. Det may be hiding around the corner. Det, is your battery fully charged?
No, it isn't.
Okay, so the green light is a bad thing.
No, because I drove it this morning and should be at something 97% or something. This would normally trigger the red LED saying I'm charging right now.
Okay, and it isn't doing, so let's have a look. So we'll measure the output voltage of this. The battery is a 42 volt battery. And we have 31.6. So
no way you can push anything.
Yep, it can't charge the battery. Another thing which kind of tells us this also, I would assume, is that even when I switch the mains off, the green LED stays on for some time. So
there's no current going on.
No current coming out. Okay, right, so let's figure out what's going on, if we can. So this is the low voltage side of the power supply. We can see there's a couple of chips on the back here. This is like the big divide between the high voltage and low voltage side. I can see what is probably a diode there. So there's going to be a diode on the secondary single voltage charging this capacitor. There's the opto isolator for the feedback for the voltage. So that will effectively, let's see where it is. Strange. Okay, so the opto isolator, if that's what it is, it looks like one, doesn't go across to the high voltage side. It's interesting. Okay. Presumably though, this is the rectifier diode, this is the large capacitor. That resistor, brown, green, silver, that's 1.5 times 0.01, so that's a 0.15 ohm resistor. That'll be current limiting, or allowing the circuit to measure the current at least. Then we have two more diodes. Now that's strange if we think that is the main rectifier, and we have, what's this thing on the end here? NCE0157A2. So let's look that up, figure out what that is, and then maybe get a better idea from there. And as we can see, this is a MOSFET. Yeah, MOSFET. Up to 57 amp. Yeah, ODS on less than 17 milliohms. Okay, so it's a MOSFET. And I think I've just realised what this is actually doing. So, without reverse engineering this at the moment, yeah, that is a diode. I can see that because if we turn it upside down, we see two pins connected to each other. Okay. So basically, this is probably a double diode with them both in parallel. Let's have a look at it. Yep, diode, like a fast diode, 0.39, fast silicon diode. Not quite a Schottky diode, but basically that. So that is the rectifier. Then we have the large capacitor. Then we have the MOSFET and these two diodes. And I'm sure now I actually know what these are doing. If we look at them, first of all, before I say anything, I'm going to check all they in parallel with each other. And they clearly are in parallel. Okay. Reads 0.16. Okay. So these are Schottky diodes. And what else do we have here? An inductor. Yeah. So this, I'm quite confident, this is a buck converter that's generating the output voltage. And where's the capacitor on the output? Well, the battery is basically like a big capacitor, really. Yeah. So that, I think, is a buck converter. Now, I know some of you are going to say, yeah, but Rich, there's only one. MOSFET and the buck converter has two. Well, that's actually not correct. So, buck converters. Yeah. Plus voltage. Pair of MOSFETs, sometimes with more than one in parallel. High side, low side. Quite possibly a low value current sense resistor in here, yeah. inductor, output capacitor to ground, okay? V out. But that ain't a buck converter. That is a synchronous converter. A buck converter would be connected like this. So plus voltage, high side MOSFET, diode, fast diode like a Schottky diode, coil, capacitor, ground. So this is synchronous, and this is a buck, okay? And this one, we know the MOSFET switch on and off alternately, first one then the other, and when this one's switched on, the current flows that way through the inductor, and when this one's switched on, it flows that way, okay? Like so, it charges the capacitor. So, and we can also have a resistor, either in there or there, I would say. When this MOSFET switches on, flows that way. When this switches off, well, the diode will conduct in that direction anyway, so passes current like that. It does the same thing. The only difference being that this one, the resistance, if you like, of that part of the circuit is the RDS on, resistance drain source on. Whereas this, it's actually the voltage drop of that diode. So this is more efficient than that, and that's basically what we might have. But there's another possibility here as well, which you should just mention, and it depends how it's wired up. We might have what's called a boost converter, which is effectively like this. So inductor, MOSFET to ground with the current sense resistor, okay, then a diode, and then normally here this is where you would have a capacitor, but I guess this could be a battery which is being charged, and that's a boost. So I'd suggest we've got one of these two, and it's quite possible that is not working properly either. Problem with the MOSFET, problem with the drive, something like that. So let's figure out if we can see which one we actually have. And clearly ours has two diodes in parallel, either here or here. Okay. The difference generally being that this one drops voltage, so V out is lower than V plus, and this one V out is higher. That's why it's a boost, okay? Let's have a look, poke around with the multimeter. Let's figure out if we have one of these two configurations, which one we have, and then from that we can have a look around to see what might be wrong with the circuit and why the voltage to the battery is too low and it doesn't show charging activity when it should be charging. We can easily work this out. We know this is the transformer coil, this is the input to the diode on the heatsink. This thing, output from the double diode goes to here. This is ground to the end of the coil, okay? And that is the large capacitor, 50 volt of 1000 microfarads. This is the positive end. This goes to the two diodes here in parallel that we can see with the cathodes towards the MOSFET. From here we can see this goes to the center pin on the MOSFET. This is the drain, okay, and then from the source of the MOSFET goes to here. And here to here, this is the inductor, and you spot this large resistor we mentioned before. Well, that's there. Reads probably close to 0. It's a 0.15 ohm. Yeah, that's actually saying 1.5, but my meter doesn't 0 very well, as you can see. Okay, goes a bit closer now. Yeah, that's the 0.15, and this comes back to the negative end of the capacitor. So that's the circuit, and then the output, which is here, this is the positive output, also connects here to the coil. Put the bleeper back on. So positive output connects to here. Yeah, that's the source of the MOSFET. And then the other end of the output connects to here, which is the negative end of the capacitor. So I've drawn that out, and we can see how we trace it through. The diode from the coil. This also goes to ground. This is your transformer secondary. Large capacitor, the two diodes in parallel to the drain. Source goes to V out, also goes to the inductor, and the current sense resistor that goes to the 0 volt. So this here is your battery, okay, and this point here is also ground. So this all connects together. Now it might look a little bit odd like that, and often when you draw these circuits, if you draw them in a different way, they appear to make more sense. So let me just do that and see what you think. So again, secondary of the transformer. A bit messy, but this is the double diode package. Okay. Again to the capacitor here. So we have a capacitor to ground. 1000 off 50 volts. Then we have the two other diodes. So we're drawing it basically the same so far. And here we'll make it look a bit different. So from here, we're going to go to the drain of our MOSFET. This is the source. This is the gate. And from the source, we have the inductor coil, the low value resistor to ground. So this is OR15, 0.15 ohms. This is a small inductor. And then this is out. And as before, your battery connects across here. Okay. So we can see clearly now that this MOSFET is just in series. Yeah. And although I don't know what this topology is called, and I had a quick look and couldn't see it. If we search for SMPS, switch mode power supply topology, one of the first links is this one, smps.us. And this shows some of the common configurations known as topology. Now, this definitely isn't all of them. We can see non-isolating converters and isolating converters. So these are what you would class as switch mode power supplies. You see a number of different topologies there. This is similar to what we would find in a basic wall wart type supply. That one, LLC half bridge. This is like the older ATX power supplies. And the ones we're interested in are the non-isolating. So these don't have a transformer. There is no isolation between the input and output voltage, just a difference in voltage. Okay. So buck converter. That's how I described it. One MOSFET, one diode, coil out with the capacitor. We don't see the synchronous converter here, which surprises me somewhat. It's like this one, but with another MOSFET here rather than the diode. We have this one, a boost converter. So this is not ours either. This is the sort of thing you find in a PFC circuit, for example. We have this one, flyback inverting or buck boost. which is more similar to ours. It doesn't show the current sense resistor, but it's not necessary unless you want to know what the current is. It has a diode here with this capacitor. Ours doesn't have that. It has diodes on the input. We have this cook, or, well, there's an accent over the C, so if that was Turkish, it would definitely be chuck. Maybe some languages it is suck, I don't know, but we have that one. I'll call it cook. This has two inductors, the diode in parallel with the MOSFET, apart from the fact there's a capacitor in between, so they're not exactly in parallel. That's nothing like ours. This one again with the two inductors, nothing like ours. So ours, if anything, is close to that one, buck boost converter. Now clearly we have a drive signal for the gate, which is here, goes across here, up to here. Haven't checked what this is, but it heads in this direction. Okay, so this is going this way. So this lot, I'm sure we can find out if we trace it through as driving the MOSFET. Makes sense. This is the current sense resistor, and again, from the end connected to the coil, we can see a track which goes off that way, heads up over here somewhere, under here, I think, around here, again goes off into that lot. So it's a guess. This is the pulse width modulation driving the MOSFET, and this is a current sense, I sense, which is either a shutdown thing if too much current's flowing, or possibly being used by the PWM controller to modify the pulse width modulation so that only a certain amount of current does flow. So when it reaches a certain point, this just ends the pulse width modulation cycle, or as I say, otherwise this can shut it down. I don't know which it is without going further. And I would say this is effectively like a boost converter. You'll notice that current flows through the inductor coil, builds up a magnetic field. Obviously same current flows through the sense resistor. When this switches off, this coil will effectively continue to conduct, and it will basically cause current to flow into the battery and charge the battery. And that is probably, depending on the width of the pulse here, going to boost the output voltage. That's how I see it. This looks like it's just there to stop this discharging back that way. Quite probably to do with the fact that this can't switch off in an instance. So when this first switches off, this may try to send current back that way, but this pair of diodes stops it from happening. Kind of like back EMF protection, but different in this circuit. So the first thing I think we can say is, if this is not switching, or not switching properly, we probably won't have enough output voltage to charge the battery. I think the first thing I'd probably just like to check is the MOSFET okay? So I will get this unsoldered, and while I'm at it, there appears to be something underneath this glue as well. So let's have a look to see what there might be here. Okay, that one. Just behind the inductor. Okay, that came out easily enough. I can see there is something behind this coil. It looks like it might be a diode. So I think, because it's possibly important to understand the circuit, I'll remove the inductor as well and then get a good look, because I'm having trouble getting the glue off from there, and it's probably no hassle to remove the inductor anyway. Okay guys, I've removed the inductor and it's not what I thought. It's not a transformer either. It's marked on the PCB, so we have basically two separate inductor coils. One end goes to the positive for the battery out, and this one is the negative end of the battery. Okay, I've just put a red mark on here and there so I know which way around it goes, but I don't think it is critical at all. So the schematic I drew is incorrect, of course. What we actually have is this. One of the inductors, V out. So this is your battery. Okay, and the other inductor is here. Yeah, the negative end of the battery. And again, the current sense still where it was. And the current for the battery flows to the current sense resistor. So that's what we actually have. This will be pulse width modulated. Again, it may use that sense to alter the modulation, not sure. And that is the circuit. So we've cleared that up. This, does it have a name? It ain't like my strange circuit, but does it have a name? And is the MOSFET any good? Although it won't be short, otherwise the full supply voltage would be on the battery, I guess. I'm guessing it probably is okay, because I can't imagine in what way it would fail that would just give me some voltage but not enough on the output. We'll see. Maybe these inductors in some way are still boosting the voltage. Okay. Or they may just be filters. So, yeah, it's good. So the MOSFET's okay. I guess the next thing we need to do then is to have a look to see what's happening on the gate. When you reverse engineer things like this, you will get it wrong. I mean, this is why I show you guys. I'm not perfect, and don't let anybody out there fool you to make you think they are. Yeah. Okay, so I've put it back together. We'll power it up. I'll put the light bulb back in just in case. You can see it over there. I've attached this wire. This is ground. Yeah, this is the safety ground, the negative end of the large capacitor. That one. So this is where I'm going to attach the ground of my oscilloscope. Yeah. I know it's red, ground. Do I care? Am I bothered? No. The electrons won't be either. Let's just make sure we still have the same output voltage we were seeing before. So watch the light bulb, guys. Yeah, that's fine. Okay, switch that out, put it on. Green LED is on. What do we see on the output? 33 volts, same as before. Okay, let's get the scope. Switch on. MOSFET gate. It goes up off the screen. Huh. Let's go to 10 times. It just has a steady voltage on it of about 30 volts, about the same as the supply voltage. Okay, so that's not doing what I would expect it to do. Let's just use the voltmeter actually, just to check the voltages on the MOSFET. So drain is 41.7. Source is 33. And the gate is also 33. Okay. So if the voltage between the gate and the source, well, 33.0, 33.03 are basically the same, then that MOSFET can't be switched on. Yeah, it's kind of like explains to some extent why we don't see much voltage on the output, but we do see some. It's not like we see no voltage on the output. Okay, so there appears to be something wrong with the drive to that MOSFET. We need to now figure out how that connects back to whatever is controlling it. Because at the moment, the source and the gate are both the same voltage. Yeah, it's an N-channel MOSFET, so the gate needs to be higher than the source to switch it on. We could trace this back from the gate, see where it goes to. But if we do that, once we've done that, we're probably going to have to figure out, because it will go to one of these ICs one way or another, what the chip is. So the other way might be, just let's have to see what these chips are, and then from that we can figure out which one most likely is driving the MOSFET, and whether it is using pulse width modulation or operating in some different way. This one I can almost read, but not quite because of this lacquer on here. The other one, yeah, I can almost read that one. Has that got a fault? Like, you know, something wrong with it there? Or is it just a blob of this lacquer? Let's get the stuff off anyway, then it'll be easier to tell. I've done this various ways in the past. My favourite technique at the moment is a plastic spudger. Put some isopropyl alcohol on. And then just rub at it, okay? This won't scratch the IC or the marking, and it sort of comes off. It like scrapes off the stuff, coating. Usually comes off in one piece or often. Just give that a moment. Let's go for this one. Can you see it there, like the coating coming off? Yeah. This being this 14-pin chip, I would not be surprised if this is like a voltage comparator, LM393 or something similar. Well, we can see a lot better now. AS324. I wonder if that's like an LM324 op amp. Quad op amp. Right size package. Could be. Would make sense for such a thing to be in this circuit. Well, this one's hard to read. I've just have a little LED torch in my hand to try and get a good angle. It looks like 084V42 -5PHM, and then something like 102104. Probably a date code, that 0421 maybe. So yeah, 084V42. In fact, I think you can see it clearer now without that light on it. Well, that number, 084V42 datasheet, brings me to this. So we have some information, IL4208. Somebody's looking for these things, basically. Some chat about it here. Somebody suggesting that they've actually sanded off the original markings and reprinted these 084V42. And that is quite correct. Yeah, so that isn't the chip number. It's been sanded off and marked. And the other one, AS324. Yeah, which says this is a industry standard 324. So this is like an LM324 op amp. So it's that other chip which is a bit of a mystery at the moment. So basically what we have is, we have a chip here which is, I'm pretty sure, LM324 quad op amp. This one has the same number marked on the chip as the model number of the charger. And it looks like it's embedded into it, like it was made like that rather than scraped off and printed. I mean, I'm not 100% sure about that, but that's what we have. I know there's 31 volts coming out of this and 31 volts on the gate to the MOSFET as well. So output on the source 31 volts, gate is 31 volts or thereabouts. They're both the same as each other exactly. Drain coming in is about 42 volts. So the MOSFET, which feeds the power to the main charge circuit, the battery, is not supplying any voltage. I've had a bit of a look around here So what I do know is that this opto isolator here, which is all on the isolated side of the supply, that's the one that gives the feedback to the high voltage side. So this opto isolator, basically the transistor in it, which is this side, kind of goes off this way, and that via a few components gets to the gate of the MOSFET. Okay, so that is driving. In fact, it goes directly, you can see, from there along here and then under there and round there and down there to the gate. So one end of the transistor in the opto isolator is controlling the gate. The other end, if you look, actually goes to a transistor, the collector here, base emitter, and it looks like that can also do something with that signal. There's a diode in here as well, so there are a number of components in that circuit. And then we have the LED side of the opto isolator. Okay, and again, there's one end of it goes to this transistor collector or MOSFET drain source. I don't know the component, and that is being controlled somewhere into this circuit and also back to here. And the other end of the LED goes through this 1K resistor and goes up to here. So it looks like pin 5 on here, or 4 and 5. No, actually pin 5 on here is something to do with controlling the LED in the opto isolator, switching it on and off. This pin 16 I actually traced goes to ground, or 0 volts of the large capacitor. And I ask myself, why would this chip be controlling the MOSFET via an opto isolator unless it's something running on a lower voltage and maybe a microcontroller? Also, the fact it's stamped with the model number of this power supply. Why? Unless it is in some way for this power supply, not for a different make. Yeah. And the last thing I notice is this is the 42 volt supply through the large diode here. There's another winding here which is not connected to that one. That feeds another voltage supply, and there's another one here feeds another voltage supply. So I honestly think the only way I'm going to figure out what this is and why this doesn't work is to reverse engineer the supply. Now, I don't think I need to reverse engineer the high voltage side. A, because it's working, and B, because it's a fairly standard switch mode power supply. There shouldn't be anything on that side that's difficult to work out what it does or repair. The problem is in this lot. So I'm going to reverse engineer this side of it. Just before I start, I'm going to measure the voltage here and the voltage here to see what the other supplies are. And then I'll show you, I've done this before, so I'll just show you the basic process without sitting through all the actual hard graft, okay? So we have, this is ground, at least for the 42 volt charging supply. And coming out of the rectifier diode, we have 41.9, okay? We can see here, this is another diode on this supply, capacitor. So here from the diode, that reads 55.9, but I'm not sure if this ground and this ground are actually really the same thing. Yeah, you see, they don't read like that. So this is the ground for this one. Just get onto it. And this is the capacitor. That's a 22 volt supply. And the other one, well, this one actually reads nothing. Maybe, oh yes, 22 volts again. So that's 22 volts with the red lead towards the diode. And that's also 22 volts with the red lead towards the diode. So maybe then this isn't a microcontroller running on a low voltage, which is why I thought the opto isolator was there. Maybe it's something else. But at least we know what voltages we have, okay? I can also see that this ground isn't the reference for the ground for that one, yeah? Also, on the opto isolator is what voltage is on the LED. So just from here to here. And that's 0. Yeah. So the LED is not being switched on. So that's why the MOSFET itself is not being switched on either. Okay. You'll understand now why datasheets are not going to help me with this one. It's a strange design, to me at least. Maybe not strange to the person who made this. There may be many others like this, but it's the first time I've come across one really. So to figure out how this works, we're going to have to reverse engineer at least part of it. That's what I'm going to do in the next video. I've already recorded most of it actually. I'm doing this little epilogue in between to let you know where we're up to. So next couple of days you'll see another video on this with the reverse engineering complete, or mostly completed, and then from that let's see if we can work out how it works and then see if we can fix it. Okay, hope you enjoyed that and I look forward to seeing you all very soon on Learning Electronics Repair. Ciao for now guys.